Welcome to the channel. Please consider subscribing. I produce videos covering AWS, Azure, and GCP on a daily basis. Please also hit the bell button to get notified. Welcome everyone. Today we're diving deep into one of the most critical aspects of securing your Google Kubernetes engine workloads. I'm going to teach you how to properly identify your resources for firewall rules, and trust me, this knowledge will save you from countless security incidents and late-night debugging sessions. I've been working with GKE for over 7 years now, and I've seen organizations make the same mistakes over and over again. They start with IP-based firewall rules because it seems simple, but then their infrastructure grows, nodes get replaced, auto-scaling kicks in, and suddenly their carefully crafted security rules become a maintenance nightmare. The three approaches we'll explore today represent the evolution of how Google Cloud thinks about resource identification. We'll start with the simplest approach that most people use, move to the production-ready standard, and finish with the enterprise-grade solution that enables true governance at scale. By the end of this session, you'll know exactly which approach to use for your specific scenario, how to implement it correctly, and how to avoid the common pitfalls that can leave your workloads vulnerable or inaccessible. The real problem we're solving. Let me tell you about a disaster that happened to me early in my career. I was managing the infrastructure for a major e-commerce platform during Black Friday weekend. We had about 200 GKE nodes handling everything from the web front-end to payment processing and inventory management. Around 2 a.m. on Friday, our payment processing completely stopped working. Customers could browse, add items to cart, but the moment they tried to check out, the system would hang. We were losing thousands of dollars per minute while I frantically tried to figure out what was wrong. After hours of debugging application code, checking database connections, and reviewing logs, I finally discovered the root cause. Earlier that evening, our autoscaler had kicked in due to high traffic and created new payment processing nodes. These new nodes got different IP addresses than the original ones. Our firewall rules were hard-coded to allow specific IP addresses to communicate with our payment database. The new nodes with different IPs were being blocked by our own security rules. This single incident cost us over $50,000 in lost sales and taught me a lesson I'll never forget. IP addresses in the cloud are like house numbers in a rapidly growing city. They change constantly as infrastructure is rebuilt, scaled, and moved around. Building security policies on IP addresses is like writing someone's address in stone when they're about to move to a different neighborhood. Network tags. When simple works. Network tags are where most people start their journey, and honestly, they're perfect for certain scenarios. Think of them like those adhesive name tags you get at conferences. They're simple, quick to apply, and everyone understands how they work. I still use network tags extensively in development environments because they strike the perfect balance between functionality and simplicity. When you're rapidly prototyping or testing new configurations, you don't want to get bogged down in complex identity management. You just want to quickly label your resources and move on. The beauty of network tags is their immediacy. You can create a tag called web servers and immediately start writing firewall rules that target it. There's no setup, no prerequisites, no waiting for permissions. It's instant gratification for network security. But here's where you need to be careful. Network tags operate on the honor system. Anyone who can edit a virtual machine can create any tag they want and attach it to any resource. I've seen developers accidentally create tags like prod database in test environments, which later caused confusion when writing firewall rules. The key is understanding when this simplicity is appropriate and when it becomes a liability. For development environments, quick prototypes, and non-critical workloads, network tags are fantastic. For production systems with strict security requirements, you'll want something more robust. Network tags architecture deep dive. Let me explain exactly what happens under the hood when you use network tags. When you attach a tag to a virtual machine instance, Google Cloud literally just stores that string of text as metadata on the instance. There's no validation, no verification, no central registry checking whether the tag makes sense. When you create a firewall rule that targets a specific tag, Google Cloud performs a simple operation. It looks at every virtual machine in your project, checks if that virtual machine has the target tag attached, and if it does, the rule applies to that virtual machine. It's essentially a string matching operation across all your resources. This simplicity is both the strength and weakness of network tags. The strength is that it's fast, easy to understand, and works immediately. The weakness is that there's no centralized control over what tags can exist or who can use them. I learned this lesson the hard way when I spent 2 hours debugging why traffic wasn't flowing between my web servers and API servers. After checking firewall rules, network connectivity, and application logs, I finally discovered that someone had used web server as a tag while I was using web server without the hyphen. Same concept, different spelling, completely different behavior. This is why I always recommend establishing clear naming conventions for tags early in your project and documenting them somewhere your entire team can access. Network tags in GKE, a practical implementation. In GKE, network tags become much more powerful. This is because you apply them at the node pool level, rather than to individual nodes. This means every node created in that pool automatically inherits the tags. And when you scale the pool up or down, all the new nodes get the same tags automatically. I typically structure my GKE clusters with different node pools for different purposes. For example, I might have a front-end pool for web servers, a back-end pool for API services, and a workers pool for background processing. Each pool gets descriptive tags that match their function. The command we're looking at creates a node pool called API server pool, and assigns the API server tag to every node in that pool. When you scale this pool from 3 nodes to 10 nodes, all 7 new nodes automatically get the API server tag. This is much more manageable than manually tagging individual virtual machines. What I love about this approach is that it creates a clear mapping between your infrastructure organization and your security policies. Your node pools represent different functional components of your application, and your tags represent the security zones those components belong to. One tip I always give to teams is to use consistent naming between your node pool names and your tag names. If you have a front-end pool, tag it with front-end servers. This makes it crystal clear what each component is for and simplifies troubleshooting when things go wrong. Examples of advanced network tags. As your applications become more complex, you might want to use multiple tags on the same resource to create more sophisticated firewall rules. This is where network tags really shine in terms of flexibility. Let me show you a real example from an e-commerce platform I worked on. We had front-end servers that needed to be accessible from the internet, but we also had API gateways that were technically front-end components, but should only be accessible from internal networks. My solution was to use multiple tags per node pool. The front-end web servers got both web tier and public-facing tags, while the API gateways got API tier and internal-only tags. This allowed me to create very specific firewall rules. For example, I could create a rule that allows HTTPS traffic from anywhere on the internet to resources tagged with public-facing, and a separate rule that allows internal API traffic only between resources tagged with web tier and API tier. The firewall rule syntax supports both in and OR logic with tags. You can create rules that apply to resources with tag A or tag B, or you can create multiple rules that effectively create and logic by requiring multiple conditions to be met. This flexibility makes network tags surprisingly powerful for complex applications, as long as you're comfortable with the security trade-offs of unverified labeling. Network tags troubleshooting. I've debugged hundreds of network tag issues over the years, and I can tell you that 90% of them come down to 3 common problems: typos in tag names, inconsistent naming conventions, and forgetting to apply tags to new resources. The verification commands I'm showing you have saved me countless hours of debugging. The first command lists all your instances along with their tags, so you can immediately see if a resource has the tags you expect it to have. I can't tell you how many times I've run this command only to discover that a virtual machine I thought was tagged with web server was actually tagged with web server or some other variation. Consistency is absolutely critical with network tags. The firewall rule listing command is equally important because it shows you exactly which tags your firewall rules are targeting. I've discovered so many duplicate rules, conflicting rules, and orphaned rules using this command. My debugging strategy is always the same. First, verify that the tags are applied correctly to the resources. Second, verify that the firewall rules are targeting the correct tags. Third, check for any overlapping or conflicting rules that might be interfering. One pro tip: always test your tag-based firewall rules in a development environment first. Create a simple test setup with a few virtual machines, apply your tags and rules, and verify that traffic flows the way you expect. This small investment in testing can prevent major production issues later. Service accounts. The production standard. When you are ready to move beyond the honor system and implement production-grade security, service accounts are your best friend. This represents a fundamental shift in thinking from labels to identities, and that distinction is crucial for understanding why service accounts are more secure. A service account is not just metadata attached to a resource. It is a real identity in Google Cloud's identity and access management system. It has permissions, it can be audited, it has a lifecycle, and most importantly for our purposes, it cannot be faked or spoofed. When a virtual machine runs with a service account, it is not just saying I am a web server like it would with a network tag. It is saying I am authenticated as this specific identity, and I can cryptographically prove it. This enables a whole new level of security architecture. I use service accounts for all production workloads because they enable true zero-trust networking. Instead of creating firewall rules that say allow traffic to anything tagged database, I can create rules that say allow traffic to anything authenticated as the database service account. The difference might seem subtle, but it is profound. With service accounts, your security policies become statements about verified identities rather than unverified labels. This makes your infrastructure much more resistant to both accidental misconfigurations and malicious attacks. Service account architecture. The architecture diagram here illustrates the key difference between network tags and service accounts. Instead of just attaching a text label, your virtual machine actually runs with a specific cryptographic identity. When Google Cloud evaluates a firewall rule that targets a service account, it doesn't just check metadata. It verifies that the virtual machine is actually authenticated as that service account using the same cryptographic mechanisms that power all of Google Cloud's security. This verification happens automatically and transparently, but it provides a much stronger security guarantee. Even if someone gains access to a virtual machine and tries to impersonate a different service account, they can't do it without the proper cryptographic credentials. What makes this especially powerful in GKE is the integration with workload identity. You can configure your Kubernetes pods to use the same service account identities as your nodes, creating a unified identity model that spans from your infrastructure layer all the way up to your application layer. This unified identity model is a game changer for security architecture. You can write policies that say the front-end application can call the backend API, and the backend API can access the database, all based on verified cryptographic identities rather than network locations or unverified tags. Service account GKE implementation. In GKE, every node pool runs with a specific service account, and this becomes the primary identity for all nodes in that pool. By default, GKE uses the Compute Engine default service account, but I strongly recommend against this for production workloads. The default service account has very broad permissions because it's designed to work with any possible workload. This violates the principle of least privilege. which is one of the fundamental concepts in security architecture. Each component of your system should have only the minimum permissions required to do its job. My approach is to create custom service accounts for each different type of workload in my cluster. For example, I might have a service account called Frontend Node SAW for web servers, another called Backend Node SAW for API services, and Workers Node SAW for background processing nodes. Each of these service accounts gets exactly the permissions it needs and nothing more. The front-end service account might need to read from cloud storage for static assets. The back-end service account might need to access Cloud SQL databases. The worker service account might need to publish to pub/sub topics. This granular approach to permissions makes your system much more secure and also makes audit trails much clearer. When you see an API call in your logs, you can immediately tell which component of your system made that call based on the service account identity. Advanced service account examples. Let me walk you through a complete service account setup for a real 3-tier web application. This is based on an architecture I implemented for a financial services company that had very strict security requirements. The front-end tier consists of web servers that serve static content and make API calls to the backend. These servers need read access to cloud storage for static assets and the ability to make outbound API calls, but they don't need access to databases or internal systems. The backend tier runs API services that handle business logic and data access. These services need to connect to Cloud SQL databases, call external APIs for things like payment processing, and possibly access other Google Cloud services like BigQuery for analytics. The database tier, which in this case was running database proxy containers in GKE, needs minimal permissions. These containers primarily just forward connections to Cloud SQL, so they only need Cloud SQL client permissions and basic logging capabilities. By creating separate service accounts for each tier with precisely the permissions they need, we created a defense-in-depth architecture. Even if an attacker compromised one tier, they couldn't easily move laterally to other parts of the system because each tier's service account has different capabilities. This approach also made compliance audits much easier because we could provide clear documentation of which components had access to what resources and why. Service account firewall rules. This is where service accounts really shine compared to network tags. Instead of creating firewall rules based on unverified labels, you are creating rules based on cryptographically verified identities. The firewall rules shown here implement a classic 3-tier architecture with perfect isolation between the tiers. The front end can only communicate with the backend can only communicate with the database, and there is no way for the front end to directly access the database. What makes this so powerful is that these rules are based on identity, not network topology. It does not matter what IPs addresses the nodes have, what subnets they are in, or even what physical data centers they are running in. The security policy is tied to the identity of the workloads. This creates what we call zero-trust networking. The network itself is assumed to be hostile, and all security decisions are based on authenticated identity rather than network location. This is a much more robust security model for cloud environments. Even if someone manages to compromise a node and gain root access, they still cannot impersonate a different service account to gain unauthorized access to other parts of the system. The cryptographic identity verification prevents this type of lateral movement. Service account troubleshooting. Service account troubleshooting is usually more complex than network tag troubleshooting because you're dealing with both configuration issues and permission issues. The most common problem I see is developers trying to use a service account they don't have permission for. The verification commands I'm showing you are essential for debugging service account issues. The first command shows you which service account each node is actually using, not what you think it should be using. This distinction is important because misconfigurations are common. I've seen cases where someone thought they were creating nodes with a specific service account, but due to a typo in the command or a permission issue, the nodes were actually created with the default service account instead. This can lead to very confusing behavior where some things work and others don't. The IAM policy listing command is crucial for understanding permissions. Service accounts are only useful if they have the right permissions for their intended purpose. I've debugged many issues where the service account existed and was properly attached to the nodes, but didn't have the necessary permissions to access required resources. My debugging approach for service account issues is systematic. First, verify the node is using the expected service account. Second, verify the service account has the necessary permissions. Third, check that the firewall rules are properly targeting the service account. Fourth, test end-to-end connectivity. One debugging technique I use frequently is to SSH into a node and run gcloudauth-list to see which identity the node is actually using. This gives you ground truth about the node's identity, which is essential for troubleshooting. Secure tags. Enterprise-grade control. Secure tags represent the pinnacle of resource identification and policy enforcement in Google Cloud. They solve a fundamental problem that large organizations face. How do you enforce consistent security policies across hundreds of projects, thousands of resources, and dozens of development teams? I first implemented secure tags at a large financial services company that had over 50 development teams working across more than 200 Google Cloud projects. They had a critical business requirement. Production financial data could never be accessible from development or staging environments. And violations could result in millions of dollars in regulatory fines. The challenge was that this company wanted to maintain developer agility and self-service capabilities while ensuring perfect compliance with their security policies. Traditional approaches like manual approval workflows or centralized firewall rule management would have created bottlenecks that slowed down every team. Secure tags solved this through what I call centralized policy definition with distributed enforcement. The security team defines the framework once at the organization level, grants appropriate permissions to development teams, and then the infrastructure automatically enforces the policies without any manual intervention. This approach enables true governance at scale. Security teams maintain control over what policies exist and who can use them, while development teams operate independently within those approved boundaries. Here's a deep dive into the secure tags architecture. This architecture diagram demonstrates the separation of duties that secure tags enable. At the organization level, security administrators define the official taxonomy of security categories that will be used across the entire organization. This is fundamentally different from network tags or service accounts, which are typically managed at the project level. With secure tags, you have organization-wide consistency in security categories, but teams can still apply those categories to their own resources independently. The IAM integration is what makes this approach so powerful. It's not just a naming convention that teams are expected to follow. It's cryptographically enforced permission controls. Development teams literally cannot use security categories they haven't been explicitly granted permission for. This creates a framework where security teams control what security categories exist and what they mean, while development teams control where those categories are applied to actual resources. But the development teams can only apply categories they've been authorized to use. The firewall policies can then be written once at the organization level using these centrally defined categories, and they'll automatically apply consistently across every project, every team, and every resource in the organization. Real-world scenario: healthcare compliance. Let me introduce you to Maria and David, who represent the two sides of the secure tags equation. This scenario is based on a real implementation I did for a healthcare company that needed strict HIPAA compliance across their entire Google Cloud organization. Maria is the Chief Information Security Officer. She has organization-level permissions, and is responsible for ensuring that the company never has a HIPAA violation. HIPAA fines can be enormous, up to $50,000 per violation. So she needs ironclad guarantees that production patient data can never be accessed from development environments. David is a senior software engineer on the patient portal team. He is responsible for rapidly deploying new features and maintaining the web application that patients use to access their medical records. He needs to move fast and cannot afford to wait for security approvals for every deployment. The company policy is simple but critical. Production environments containing PHI can never be accessed from development or staging environments. Any violation is a potential HIPAA breach that could cost the company millions of dollars and damage their reputation. The challenge is enabling Maria to enforce this policy across 50-plus development teams and 200-plus projects while allowing David and his peers to deploy applications quickly without getting bogged down in security approval processes. Step 1. Finding your organization ID. Before Maria can create any secure tags, she needs to identify her organization ID. This is the foundation for everything that follows. Secure tags are created at the organization level, and they inherit down to all projects. Many people work with multiple Google Cloud organizations, so it is important to be absolutely certain you are working with the right one. The G Cloud Organizations List command shows all the organizations Maria has access to. In this case, Maria can see 2 organizations: Healthcare Corp with ID, and Regional Medical Group with a different ID. She needs to use the Healthcare Corp organization, so she will use the Healthcare Corp organization ID in all her subsequent commands. This organization ID will appear in every secure tag command going forward. It is like the root address that tells Google Cloud where to create and manage the tags. Make sure to copy this ID exactly. Any typo will cause your commands to fail. Pro tip: I always save the organization ID in a text file when I am doing secure tags implementation. Because you will need to type it many times, it is easy to make mistakes with these long numbers. Step 2. Creating the tag key. Now Maria creates what Google calls a tag key. This is like creating a new category for classifying resources. She chooses environment because she wants to categorize all resources by whether they're production or development. The G Cloud Resource Manager tags keys create command takes the organization ID we found in the previous step as the parent. This tells Google Cloud that this tag key belongs to the Healthcare Corp organization and will be available to all projects within that organization. Notice that Maria adds a description explaining that this is for HIPAA compliance. This might seem optional, but 6 months from now, when someone is trying to understand why this tag exists, that description will be invaluable for governance and audit purposes. The command returns a unique tag key ID, in this case tag keys /. This ID is what Maria will use as the parent when creating tag values in the next step. The short name environment is what developers will see and use in their deployment commands. This tag key creation is irreversible in production environments. Once teams start using it, you can't delete it. So choose your tag key names carefully and make sure they align with your organization's long-term governance strategy. Step 3. Creating production tag value. Now Maria creates the first allowed value under the environment tag key, prod, for production resources. This is where the real security control happens, because she is defining exactly which environment types can exist in the company. Notice that she uses the tag key ID from the previous step as the parent. This creates a hierarchy. The organization contains the tag key, and the tag key contains the tag values. This hierarchical structure is what enables the powerful governance capabilities of secure tags. The description clearly states that this is for production environments with PHI data. This makes it crystal clear to everyone in the organization what this tag value represents and why it exists. Remember, PHI is protected health information under HIPAA regulations. The command returns another unique ID, tag value /, which Maria will need when granting permissions to David's team. This ID represents the specific prod value under the environment key in the Healthcare Corp organization. By creating this tag value, Maria is essentially creating an official security clearance level that can only be used by teams she explicitly grants permission to. No one can just make up their own production environment. They have to use this official one. Step 4. Creating development tag value. Maria now creates the second allowed value, the value dev, for development resources. This completes her environment taxonomy and ensures that there are exactly 2 official environment types in the organization. The key insight here is what Maria is not creating. She's not creating values like staging, test, prod-like, almost production, or any of the creative environment names that developers sometimes come up with. By limiting the options to exactly prod and dev, she eliminates potential security gaps. The description emphasizes that development environments should not contain PHI data. This is crucial for HIPAA compliance. Development teams should only work with synthetic or anonymized data, never real patient information. This command returns another unique tag value ID, which represents the dev value. Now Maria has both tag value IDs she needs for the final step of granting permissions to development teams. The beauty of this approach is that it prevents policy circumvention through creative naming. Developers can't accidentally or intentionally create unofficial environments that might bypass security controls. Step 5. Granting production tag permissions. This is the most critical step in the entire process. Granting David's team permission to use the production tag, without giving them permission to create or modify tags. This is the essence of centralized control with distributed usage. Maria uses the tag value ID for production that was returned in Step 3. She grants the roles/resource manager.tag user role to the group patient portal team at healthcarecorp.com. This is a very specific permission that allows the team to attach this exact tag to resources they own. Notice that she is granting permission to a Google group rather than individual users. This is a best practice because team membership changes frequently, and managing individual permissions does not scale in large organizations. The tag user role is carefully designed. It does not allow creating new tags, modifying existing tags, or even using other tag values. David's team can only use the specific environment equals prod tag that Maria has granted them permission for. This creates the perfect balance of security and agility. David can deploy production resources immediately using the approved tag, but he cannot accidentally or intentionally bypass security policies by creating unauthorized tags. Step 6. Granting development tag permissions. Maria now grants the same team permission to use the development tag. This allows David's team to deploy both production and development resources using the appropriate official tags. By granting both prod and dev permissions to the patient portal team, Maria enables them to manage their complete application lifecycle. They can deploy development versions for testing and production versions for live patient access, all within the approved security framework. Some organizations choose to grant different teams different tag permissions. For example, junior developers might only get access to dev tags, while senior engineers get both dev and prod access. The flexibility is there to match your organizational structure. The command returns confirmation that the IAM policy has been updated. At this point, David's team can start using both environment tags immediately. They don't need to wait for any additional approvals or setup. Maria's work is now complete. She has created a secure, auditable framework that will automatically enforce HIPAA compliance across the entire organization while enabling development teams to work independently within approved boundaries. Verification. Checking tag keys. After creating the tags, Maria should verify that everything was set up correctly. This verification step is crucial because once teams start using these tags, fixing mistakes becomes very difficult and disruptive. The G-Cloud Resource Manager Tags Keys List command shows all tag keys in the organization. Maria can see that her environment tag key was created successfully with the correct ID and description. Notice the namespace name field. This shows the fully qualified name followed by /environment that developers will use in their deployment commands. This format ensures global uniqueness and prevents conflicts between different organizations. The create timestamp provides an audit trail showing exactly when this tag key was created. This is important for compliance reporting and incident investigation. If Maria sees any unexpected tag keys in this list, or if her tag key is missing, she knows there's a problem that needs to be fixed before proceeding to grant permissions to development teams. Verification. Checking tag values. Maria also needs to verify that both tag values were created correctly. The G-Cloud Resource Manager Tags Values List command shows all values under the environment tag key. She can see both prod and dev values with their unique IDs and descriptions. The namespace dnames show the fully qualified formats that developers will use: environment/prod and environment/dev. This verification is important because these tag value IDs are what Maria used when granting permissions. If the tag values weren't created correctly, the permission grants would have failed. The output also serves as documentation for Maria's team. She can share this list with developers to show them exactly which tag values are available and what they're intended for. At this point, Maria has successfully created a complete secure tags framework. The next slides will show how David uses this framework to deploy applications while staying within the security boundaries Maria has defined. David's production deployment. Now we switch to David's perspective. He needs to deploy a production GKE cluster for the patient portal application. Because Maria has already granted him permission to use the production tag, he can do this independently without waiting for security approval. Notice how David uses the fully qualified secure tag format, which includes the organization ID/environment/prod. This tells Google Cloud exactly which tag he wants to apply: the prod value under the environment key in the Healthcare Corp organization. The cluster and node pool names are descriptive and clearly indicate this is for production use. David uses appropriate machine types and node counts for a production workload that will handle real patient data. When this command succeeds, every node in this pool will automatically have the environment equals prod secure tag applied. This means they'll be subject to Maria's firewall policies that govern production resources. The beauty of this approach is that David doesn't need to think about security policies. He just uses the appropriate tag for his deployment, and the infrastructure automatically applies the right security controls. David's development deployment. David also needs a development cluster for testing new features before they go to production. He uses the same basic command structure but with the development tag instead. Note that he uses smaller machine types and fewer nodes for the development cluster. This makes sense because development workloads typically don't need the same resources as production systems. The secure tag, environment, dev indicates that this is a development system meant only for synthetic data, never real patient information. When Maria's firewall policies are in place, this development cluster will be automatically prevented from accessing production databases or other production resources. The security isolation happens at the network level without any application changes. This gives David the freedom to experiment and test in development without any risk of accidentally accessing or corrupting production patient data. What happens when David steps outside boundaries? This slide shows what happens when David tries to use a tag he doesn't have permission for. This is one of the key security features of secure tags. They fail fast with clear error messages when someone tries to bypass the approved framework. David attempts to create a staging environment, but he doesn't have permission for this tag value. Even if the staging tag value existed, David's team wasn't granted permission to use it. The error message is clear and actionable. It tells David exactly what went wrong, what permission he's missing, and who to contact for access. There's no ambiguity or silent failure that could lead to misconfigurations. This fail-fast behavior is crucial for security. It prevents developers from accidentally creating resources without proper tags, and it prevents malicious actors from bypassing security controls. The error also provides Maria with an audit trail. She can see in the logs when someone tried to use unauthorized tags, which helps her understand if the current tag taxonomy meets the organization's needs or if adjustments are required. Maria's firewall policy implementation. This is where all of Maria's setup work pays off. She creates a single firewall policy at the organization level that automatically enforces security requirements across every project and every resource in the organization. The policy named Healthcare HIPAA Policy clearly indicates its purpose. The three rules work together to create perfect environment separation. Production systems can talk to production systems, development systems can talk to development systems, but there's absolutely no cross-environment communication. Rule 1000 allows communication between resources that both have the environment equals prod tag. This enables the patient portal web app to talk to the production database, for example. Rule 1100 allows communication between resources that both have the environment equals dev tag. This enables development testing with synthetic data. Rule 2000 is the critical security control. It explicitly denies traffic from development resources to production resources. This prevents any accidental or intentional access to real patient data from development systems. What makes this powerful is that these rules are enforced automatically by the infrastructure. David doesn't need to think about firewall rules when deploying applications. The network simply enforces Maria's security policies based on the tags. This final architecture diagram shows the end result of our secure tags implementation. We have perfect environment separation automatically enforced by the infrastructure itself, with no possibility of human error or oversight. David's production web application can communicate with the production database because they both have the env equals prod tag. The system automatically allows this communication based on the policy Maria defined. His test application is automatically blocked from accessing production data because the tags don't match. The firewall policy sees a request from env equals dev, trying to reach env equals prod, and blocks it as a potential HIPAA violation. What makes this beautiful is that it happens transparently. David doesn't need to think about firewall rules, security policies, or compliance requirements when he's deploying his applications. He just uses the appropriate tags for his resources, and the infrastructure automatically applies the right security controls. From a compliance perspective, this provides Maria with the audit trail and assurance she needs. Every resource is clearly labeled with its environment and data classification. Every communication is logged and auditable, and the policies are automatically enforced without any possibility of human oversight. The automated enforcement also eliminates the most common source of security incidents: human error. There's no way for someone to accidentally configure a firewall rule incorrectly or forget to apply security controls to a new resource. The policies are baked into the infrastructure itself.